Hey guys, Dr. Brown here with Kubo Math coming to you from Tarlac City, Philippines. And tonight it's Calculus 1, a differentiation problem. We have a rocket and we're trying to figure out how fast this guy's going. So let's dig into it. Okay, don't laugh. I told you I have no artistic ability. That's a rocket. It looks like an upside down flashlight flying through the air. Okay. They have a radar tracking station, and it's 2 miles from where the rocket launched. So this rocket's launched 2 miles from the tracking station. And the question thereafter is when the rocket gets up to 50 degrees from the tracking radar, at that instant, what's the speed of the rocket? Now, they also give us one piece of more information here. They tell us that the rocket is going up at 5 degrees per second. So it's moving pretty quick, okay? So how quick is that? So if they're wanting the speed of the rocket, well, that's going to be dy dt, the rise or change in that height with respect to time. Okay, what to do? Well, first let's change this to radians. Let's just get that out of the way before we go any further. When you change to radians, there's just a small formula I just try to remember. I'll have 180 degrees over pi, and that's degrees over radians. That's the way I write it. So radians, I just solve for that because that's what I want to know. Radians equals the degrees times pi divided by 180 degrees. So I have 5 degrees times pi divided by 180 degrees. So that number of radians, and I have a few key things written over here, that's 8.73 times 10 to the minus 2. Oh, and this would be, since it's degrees per second, we end up with that many radians per second. Okay? All right, let's just hold that thought for just a moment. You probably hear the rooster crowing in the background. It's 1:30 in the morning. Import chicken, I guess. His time scale is messed up. There he goes. All right. Okay, let's solve a few more things here, or write a general equation. Why don't we do that? We've got tangent of alpha, and that equals the opposite over adjacent. So that equals y over 2, and both of those are in miles. Okay, so since we're looking for dy, let's go ahead and move the 2 over. So I'm going to multiply both sides by 2. So 2 miles tangent alpha equals y miles. Okay. Well, let's go ahead and just take the derivative with respect to time. Okay. So my 2 miles, that's a constant. Derivative of tangent is secant square alpha d alpha dt, and that equals dy dt. Well, remember we had d alpha dt right here, so I have that piece. Secant squared of alpha. Well, in order for me to determine secant square of alpha, which, you know, it's the opposite of cosine. So cosine is the adjacent over hypotenuse. Well, secant is hypotenuse over adjacent. Well, I don't know the hypotenuse, so I need to get that. In order to get that, which would be the square root of y squared plus x squared, and the square root of the sum. Well, we know x, but I don't know y. That's how I know y, I know x, but I don't know the side y. Okay, x was given, just a joke. All right, let's see. So y, well, let's go back to this equation here. So tangent, we would be here, so that equals y. So 2 miles times tangent of 50 degrees, which is where we were at the instant of concern. So that's 2 miles, and that equals y. A tangent of 50 was 1.19. So if I multiply those together, I get 2.38 miles. So y is 2.38 miles. Okay. All right, keep my little spot clean here for work. Okay, we're slowly getting there. Now, let's go ahead and solve for the hypotenuse. So we have 2.38 miles squared plus 2 miles squared, the square root of that. So if I go ahead and do that, let's see, I've got that over here somewhere. That equals 3.11 miles. So I have miles squared plus miles squared. The square root of miles squared would be miles. So 3.11 miles. All right. So now then, we could plug everything in here. I believe we have it all. So we have 2 miles times secant, and you know this is secant alpha squared. That's sort of an odd nomenclature there. So I have 3.11 divided by 2, and these are both in miles. 2 miles, miles cancel, and that's going to be squared, times d alpha dt, which is 8.73 times 10 to the minus 2 radians per second. Okay, so if we go through all of that, I still have miles per second, are the only units I have left. I get 0.42 miles per second. Well, you may be thinking, okay, how many miles per hour is that? Fair question. Okay, we know there's 3,600 seconds per hour, but if you don't know that, you know there's 60 seconds per minute, and you know there's 60 minutes per hour. Seconds and seconds cancel, minutes and minutes cancel. I'm left with miles per hour, and this comes out to about 1,512 miles per hour. That would be how fast that rocket, the flying flashlight, is going at the instant we get 50 degrees. Now, if you could do this algebraically, but you can't look at the instantaneous rate of change. I worked this earlier before I did the calculus piece. I thought, well, what would the answer be if I did it just algebraically? And I said, well, I'm at 45 degrees, so what was y? So I had a number. And then 5 degrees later, which was a second later, I'm at 50 degrees. So I looked at delta y and looked at, I went that delta y in 1 second. And I don't remember the exact number, but it was, I think, around 1,350 or something like that. That's the beauty, though, of doing it with a calculus, looking at, you know, you're looking at the derivative of these with respect to time instead of delta y. So a little, just a, you know, it's a smidget of a difference between those, but it is a difference. But if you never had calculus and you had to estimate that, that would be a way to do it. It would just be ultimately incorrect, but it'd be close. Okay, just a simple problem, the flying flashlight, or my rocket, and just an example of how to use derivatives. I did go back today, and I went back to an old textbook that I had in college years ago, calculus textbook, and it's noticeably more full of word problems than one I'm using currently. That's a new textbook, and actually, I think the old school way of, it's full of word problems is the point, and the one today in today's version is not. The old school one was more, here's the hand, can you learn this with the pencil, piece of paper, and a calculator? Mainly no calculator, versus today was use a graphing utility to determine the minimums and maximums, to determine inflections. I don't know which is the best way. I know AI and all the new technologies are coming on, and people need to prepare for that. But in my mind, if you can't work it with a pencil and piece of paper, at least understand the concepts. Now, obviously, you grow into that computer side of it, but learn the pencil paper piece first and get, hey, I understand what's happening, and then grow into the graphing utilities and the AI side of it. I would encourage you to do that so that in your mind you have a good understanding of what that computer system is doing. Okay, that's all for now. I appreciate this. Why are we doing it? Hey, we're trying to build a better tomorrow and do that through math. And I have a little saying at the bottom here. Today is the day you make a difference. Seize the day. I tell myself that every single day. Actually, there's 4 sayings that I tell myself. That's just one of them. But I try to be a glass half full kind of guy, and I want to share that with you. Pass it on. Be positive. Whatever deck of cards you've been dealt in life, hey, play that hand, okay? Optimize yourself. Be the best you can be. Seize the day, okay? All right, that's all for now. We'll talk to you next time. Thanks.